So here we're going to talk about so-called closest packed structures. And to illustrate, we're going to start out with something that is not closest packed. Let's say we have a layer of tennis balls and we want to put them in a box. And the next layer, let's say we put the next layer of tennis balls directly over the first layer. And we put the next layer on top of that directly on top of the previous ones. So you can see that these guys all line up and these fellows all line up, etc. Well, that is a type of close packed structure, often referred to as a cubic close packed, because if we look at the alignment, we get something like a cube. We'll have a diagram where we've separated the atoms a bit. Of course, in this diagram up here, they're all touching. Here, we're not showing them touching, but we have this vertical alignment where these guys are directly on top of one another. But that's not the closest possible way to arrange the atoms. If we take a layer here, instead of putting one right here, we could instead take a series of atoms and take advantage of that divot and then put them over here. So our next layer can be a little bit more closely packed than in this case over here. So we've saved a little bit of the space by taking advantage of those divots. And we could do the same thing over here. We could take advantage of the divots and then put atoms over here. And depending on how we take advantage of those divots, we could do it in repeating layers, where we have an A layer shown here in orange, and then a B layer shown here in green, and then this is also an A layer because it's directly above these guys. So these are in analogous positions. So we just really have two layers that are repeating over and over again. And in that case, we call it a hexagonal closest packed, or HCP. And it comes from the fact that if you start connecting atoms with bonds, you can work out a hexagonal type structure. Another way of doing this, I'm not going to try to draw because of this very nice figure from Dexter Perkins' online textbook, is we can have the A layer in orange again here. We can have a B layer, which is shown in green here, but we can have a distinct C layer. Again, it's taking advantage of divots, but a separate set of divots. So in this case, we get three layers, an ABC structure, and in that case, we call it a CCP structure, or cubic closest packed. And it's cubic closest packed because you can work out a face-centered cubic structure as shown here. And then another type of close packed, not necessarily closest packed, is if we come back to this cubic case here. So this fellow here, we'll just call this cubic closed packed, not closest packed. We can take an atom and put it in the center, and then that would give us a so-called BCC, or body-centered structure. We've got a body of a cube, and then we've put something in the center of it, so hence the name body-centered, or BCC. Again, that is not a closest packed structure, but it is a close packing of the atoms. And then it gives us this particular, or this would be a cesium chloride structure, for example, this case here. So we have different kinds of ways of packing atoms together, especially if they're all the same size. And this is not going to happen with a lot of ionically or even many covalently bonded substances, but for metals and perhaps even some sulfides or sulfur salts, oxides, etc., this kind of close packing might be approximated depending on the size of the atom. If the atoms are very different in size, then this entire packing structure is off, and instead we would look at so-called radius ratios, as we explain in looking at Pauling's rules and his rule of the coordination principle.